Welcome to this walkthrough of LeetCode problem number 1430. Check if a string is a valid sequence from root to leaves path in a binary tree. In this session, we'll explore the problem, break it down step by step, and discuss different approaches to solve it. Let's dive in. In this problem, you are given the root of a binary tree, which is a hierarchical data structure, and a sequence of integers represented as an array. Your goal is to determine whether this sequence corresponds to a valid root to leaf path in the binary tree. For the sequence to be valid, it must meet three conditions. First, it must start at the root node of the tree. Second, each value in the sequence must match the value of the corresponding node as you traverse down the tree. Finally, the sequence must end at a leaf node, which is defined as a node without any children. The input to the problem consists of the binary tree's root and the sequence array, and the output will be a Boolean value, true if the sequence is valid, and false otherwise. Let's look at an example to better understand the problem. Suppose we have a binary tree with the given structure in the sequence array 0, 1, 0, 1. Here, the tree starts with the root node having a value of 0, which branches into two children, one with the value 1 and the other with the value 0. As we move further down the tree, we see that the path corresponding to the sequence 0, 1, 0, 1 exists. Starting from the root, the first value matches the root node's value, the second value matches the left child, the third value matches its left child, and the fourth value matches the left child of that node. Since this sequence reaches a leaf node and adheres to the tree's structure, the output for this example is true. Now let's consider another example with the same binary tree, but this time the sequence array is 0, 0, 1. Here, we start at the root, which matches the first value of the sequence, and move to the right child with the value 0, which matches the second value. However, there is no child node with the value 1 to continue the sequence. This means that no root to leaf path in the tree matches the sequence 0, 0, 1. As a result, the output for this case is false. This example highlights that a valid sequence must traverse down the tree without skipping any nodes and must reach a leaf node. In a third example, the sequence is 0, 1, 1. Starting at the root node with the value 0, we move to the left child with the value 1, and then to its right child, which also has the value 1. While this sequence matches the structure of the tree, it does not end at a leaf node. The node with the value 1 has a left child, which means it is not a leaf. For a sequence to be valid, it must terminate at a leaf, and since this condition is not met, the output is false. This illustrates the importance of the sequence ending at a node with no children. When solving this problem, there are several key observations to keep in mind. First, the task requires traversing the tree while simultaneously validating the sequence. This can be achieved using a recursive depth-first search or an iterative approach with a stack. Additionally, verifying whether the sequence ends at a leaf node ensures that it adheres to the requirements of the problem. In terms of complexity, the time taken to traverse the tree is proportional to the number of nodes, O(n), while verifying the sequence is proportional to its length, O(k). Therefore, the overall time complexity is O(n)(k). The space complexity is determined by the height of the tree, which, in the worst case, can be O(n) if the tree is highly unbalanced. To solve the problem of checking if a sequence is a valid path from the root to a leaf in a binary tree, one approach is to use a recursive depth-first search, or DFS. The intuition behind this method is straightforward. We start at the root node and traverse down the tree, matching the sequence values step by step. At each node, we check if its value matches the current sequence index. If it does, we proceed to its left and right children, advancing the sequence index. If we reach a leaf node and the sequence has been fully matched, we know the sequence is valid, and we return true. On the other hand, if there's a mismatch at any point, we can stop exploring that path. A key observation here is that the sequence must align perfectly with the path from root to leaf, no gaps or skips are allowed. Additionally, a valid leaf node must have no children and must correspond to the final index in the sequence. In terms of complexity, the time is proportional to the number of nodes in the tree, O(n), since we may visit every node. The space complexity is O(h), where h is the height of the tree, due to the stack frames created by recursion. An alternative to the recursive DFS is an iterative DFS using a stack. Here, instead of relying on the system's call stack, we create a manual stack to store each node along with the sequence index we are trying to match. This approach allows us to simulate depth-first traversal without recursion. The logic remains the same. At each step, we pop an element from the stack, compare the node's value to the sequence, and push its children onto the stack if they align with the next sequence index. This method is particularly useful in environments with limited stack memory, as it avoids recursion. The time complexity remains O(n), as every node is processed once, and the space complexity is still O(h), since the stack size is proportional to the height of the tree. Another option to consider is the breadth-first search, or BFS. Using BFS, we traverse the tree level by level, using a queue to store nodes and their corresponding sequence indices. At each step, we dequeue a node, verify its value against the sequence, and enqueue its children with the updated sequence index. If we find a leaf node that matches the final sequence index, we return true. However, BFS does not offer any clear advantages for this problem. While it ensures layer-by-layer traversal, it is less memory efficient than DFS for deep trees due to the large queue size required. After evaluating these approaches, the optimized strategy we chose is the recursive DFS. This approach is a natural fit for the problem because it directly aligns with the goal of validating a root-to-leaf path. Recursive DFS is simple to implement, and its space complexity is optimal for skewed trees, where the height is smaller than the width. While iterative DFS avoids recursion, it introduces additional complexity in managing the stack manually without any significant performance gain. BFS, on the other hand, does not align well with the sequential, path-specific nature of this problem and is less efficient in terms of memory for deep trees. One trade-off of recursive DFS is the reliance on the system stack, which could result in stack overflow for extremely deep trees. However, given reasonable input constraints, this is rarely an issue. Ultimately, recursive DFS balances simplicity and performance, making it the most intuitive and effective solution for this problem. Its minimal trade-offs allow us to solve the task efficiently while keeping the implementation clean and focused on the root-to-leaf traversal logic. To solve this problem, we need to determine if there exists a path in a binary tree that matches a given sequence. The path must begin at the root and follow parent-to-child connections all the way to a leaf node, aligning exactly with the sequence. To break this down, we start by initializing the search. The algorithm begins at the root node of the binary tree and the first index of the sequence. If the tree is empty, meaning the root is null, we can immediately return false since there's no path to match. Next, at each step, we validate the base conditions. If the current index of the sequence exceeds its length, it's impossible to match, so we return false. Additionally, we check if the value of the current node matches the sequence value at the current index. If it doesn't, that path cannot be valid, and we return false to terminate further exploration down that branch. Now, we handle the case where we reach a leaf node. If the current node has no children and the current index is the last position in the sequence, we check if the node's value matches the sequence at this index. If it does, we return true because we've successfully found a valid path. Otherwise, we return false, as the path doesn't fully align with the sequence. After handling leaf nodes, we proceed with recursive traversal. At this point, the algorithm explores both the left and right subtrees of the current node, advancing the sequence index by 1 for each recursive call. If either the left or right subtree returns true, we know a valid path exists, so we propagate that result up the recursion stack using a logical OR. Finally, the algorithm starts recursion from the root node in sequence index 0, returning the result of the recursive function to determine whether the sequence matches any path in the tree. This algorithm is built on the foundation of a depth-first search, which systematically explores all potential paths from the root to the leaves. By iterating through the sequence incrementally, the algorithm ensures that each node is checked against the corresponding index in the sequence, avoiding unnecessary computations. A key aspect is the explicit handling of leaf nodes. This guarantees that only complete paths matching the sequence are considered valid, preventing partial paths from being incorrectly counted as solutions. Additionally, the algorithm is optimized to terminate early for invalid paths. For instance, if a node's value doesn't match the sequence or the sequence index exceeds its length, the algorithm stops exploring that branch. This optimization significantly reduces redundant calculations and ensures efficient traversal of the tree. The algorithm relies on two primary data structures. First, the binary tree, which consists of nodes, each containing a value and pointers to their left and right children. This structure allows for efficient navigation through parent-to-child relationships. Second, the sequence is represented as an array, enabling constant time access to its elements during the matching process. In terms of complexity, the time complexity is O(n), where n is the number of nodes in the tree. This is because, in the worst case, we may visit every node once. For space complexity, the primary factor is the recursion stack depth. In the worst-case scenario, such as in a skewed tree, the stack depth is O(n). For a balanced tree, the depth is reduced to O log n, reflecting the height of the tree. Together, these considerations highlight the algorithm's efficiency and scalability for this problem. This solution implements the isValidSequence function to check if a given sequence matches any root-to-leaf path in a binary tree. The algorithm begins by checking if the binary tree is empty. If the tree is empty and the sequence is also empty, len arr equals 0, the result is valid. Otherwise, it defines a helper function DFS to perform a depth-first search recursively. 1. Base case for null nodes. If the current node is none, it returns false since no further path exists. 2. Out of bounds or value mismatch. If the index exceeds the sequence length or the current node's value doesn't match the sequence value at the current index, it terminates the current path by returning false. 3. Leaf node check. If the current path reaches the last index of the sequence and the node is a leaf, no children, the function returns true, indicating the sequence matches. For recursive calls, if none of the above conditions are met, the function recursively checks the left and right subtrees using DFS, node.left, index +1, and DFS, node.right, index +1. If either path leads to a valid sequence, it returns true. Finally, the algorithm initiates the DFS from the root node with the first index of the sequence. The recursive traversal ensures that all possible root-to-leaf paths are checked against the sequence, guaranteeing correctness. This solution handles edge cases such as empty tree and sequence, mismatched sequence lengths, nodes with null children, valid sequences ending at leaf nodes. The time complexity of this solution is O(n), where n is the total number of nodes in the tree, as each node is visited at most once. The space complexity is O(h), where h is the height of the tree, because of the recursive call stack. Here, we begin with the class definition for our solution. Inside the solution class, we define a nested static class called TreeNode, which represents the nodes of our binary tree. Each tree node has an integer value, a reference to its left child, and a reference to its right child. There are two constructors provided, one for creating a node with just a value, and another for creating a node with a value, a left child, and a right child. Next, we define the main method, isValidSequence, which takes the root of the binary tree and an integer array, arr, as input. This method checks if there exists a root-to-leaf path in the tree that matches the sequence in the array. If the root is null, we immediately return whether the array is empty. Otherwise, we delegate the task to a helper method named DFS, passing in the root node, the array, and an initial index of 0. The DFS method is a recursive helper function that handles the depth-first traversal of the binary tree. First, we check if the current node is null. If it is, we return false because a null node cannot be part of a valid sequence. Next, we verify if the current index is out of bounds of the array or if the value of the current node does not match the corresponding value in the array. If either condition is true, we return false. After that, we check if we've reached the last index of the array and if the current node is a leaf node, meaning it has no left or right children. If both conditions are satisfied, we return true because we've found a valid sequence. Finally, we recursively call DFS for both the left and right children of the current node, incrementing the index by 1, and return true if either recursive call identifies a valid sequence. Here, we have a binary tree and an array. The goal is to determine if the array represents a valid sequence of node values from the root to a leaf. Starting with the initial call to the function, we pass the root of the tree and the array to isValidSequence. The root node has a value of 0, which matches the first value in the array, so we proceed to the helper function DFS, where we begin at the root and index 0. At the first node, the values match, and since we're not at the last index, we continue by exploring the left child. Moving to the left subtree, the next node has a value of 1, which matches the second value in the array. Again, the index is not at the end, so we recurse further into the left subtree. In the next step, we reach a node with a value of 0, which matches the third value in the array. We continue further into the left child. Finally, we reach a leaf node with a value of 1, which matches the last value in the array. Since this is a leaf and we've matched every value in the array, we return true. The left subtree validates the sequence, so we don't check the right subtree, and the final result for this example is true. In this example, the array has an extra element, making it longer than any valid path in the tree. The process begins the same way as before, with the root node being checked against the first value in the array. The values match, so we proceed to the left subtree. The left child has a value of 1, which matches the second value in the array. We then move further into the left subtree, where the next node has a value of 0, which matches the third value in the array. At this point, we proceed to the left child again and reach a leaf node with a value of 1, which matches the fourth value in the array. However, even though this is a leaf, the array still has one more element, 2, which cannot be matched. This makes the sequence invalid. Since the extra element in the array prevents it from being a valid sequence, the function returns false, and the final result for this example is false. In this example, the issue lies in a value mismatch between the array and the binary tree. The process begins as usual, with the root node being checked against the first value in the array. The values match, so we proceed to the left child. At the left child, the value matches the second value in the array, so we continue further into the left subtree. However, the next node has a value of 0, which does not match the third value in the array, which is 1. This mismatch invalidates the left subtree path, so it is not a valid sequence. When we check the right subtree, no valid path matches the array either. As a result, the function determines that there is no valid sequence corresponding to the array, and the final result for this example is false. To analyze the time complexity of our solution, let's first consider the depth-first traversal of the tree. The algorithm uses a DFS approach to explore every path from the root to the leaves. In the worst-case scenario, where the binary tree contains n nodes, we may visit each node exactly once. This means the traversal alone contributes O(n) to the time complexity. Next, at each node, we perform a simple comparison to check if the node's value matches the corresponding value in the array ARR. Since this comparison is a constant time operation, or O(1), and we make it for each node, the cumulative cost of these comparisons also adds up to O(n). Finally, we account for the recursion depth, which corresponds to the height of the tree, denoted as h. In the worst case, such as in a skewed tree, the height is equal to the total number of nodes, so h equals n. For a balanced binary tree, the height is approximately O log n. Therefore, the recursive calls contribute O(h) to the time complexity. When we combine these factors, the overall time complexity of the algorithm is O(n) in the worst case, where n is the total number of nodes in the tree. Now, let's analyze the space complexity of our solution. The primary factor here is the memory used by the recursion stack. The recursion depth depends on the height of the binary tree, which is represented by h. In the worst-case scenario of a skewed tree, the height is equal to the total number of nodes, so the recursion stack can grow up to O(n). In the best-case scenario of a balanced binary tree, the height of the tree is approximately O log n, meaning the recursion stack would contribute only O log n. Additionally, this algorithm does not use any extra data structures to hold intermediate results. The input array ARR remains unchanged and does not require additional memory allocation. As a result, the additional space usage is O(1). When we combine these factors, the overall space complexity is O(h), where h is the height of the binary tree. This evaluates to O(n) in the worst case and O log n in the best and average cases. Let's compare our approach to a naive one to highlight its efficiency. A naive approach might involve generating all possible paths from the root to the leaves of the tree and then comparing each path with the array ARR. However, generating all paths is computationally expensive because the number of paths can grow exponentially with the number of nodes. For a tree of height h, this would result in a time complexity of O2 to the power of h. On the other hand, the current DFS approach is much more efficient. It avoids generating unnecessary paths and terminates early whenever a mismatch with the array is detected or when the array is fully matched. By doing this, the algorithm ensures a linear time complexity of O(n), which is significantly better than the exponential complexity of the naive method. Finally, let's break down the best, average, and worst-case scenarios of our algorithm. In the best case, if the root node's value does not match the first element of the array ARR, the algorithm terminates immediately. Here, the time complexity is O(1). In the average case, for a balanced binary tree, the algorithm explores paths proportional to the tree's height, which is O log n. The recursion stack in this scenario also grows to O log n. In the worst case, such as in a skew tree, the algorithm explores all n nodes, resulting in a time complexity of O(n) and a space complexity of O(n) due to the recursion stack. Mathematically, the DFS traversal ensures that each node is visited at most once, with each visit involving constant time operations. This guarantees that the computational cost is proportional to the number of nodes, confirming the O(n) time complexity. Similarly, the recursion stack's growth is dictated by the tree's height, leading to an O(h) space complexity. These results align with the properties of binary trees and the problem's constraints. When solving this problem, there are a few common mistakes to watch out for. First, not handling edge cases properly can lead to runtime errors. For instance, if either the tree is empty or the sequence is empty, the program might try to access invalid indices. To avoid this, always validate your inputs at the start of the function. Another mistake is inefficient traversal, where nodes are redundantly visited even when it's already clear that the sequence cannot match from a given path. To fix this, implement early termination by returning false as soon as you detect a mismatch. Additionally, mismanaging the index in the sequence is a frequent pitfall. If you skip or reuse indices incorrectly during recursive calls, it can lead to wrong results. Be careful to pass the correct sequence index at every step to avoid unintended behavior. Now, let's consider two more common errors. One is ignoring leaf node constraints. In problems involving paths in a binary tree, it's crucial to verify that the path ends at a leaf node. Without this check, you might incorrectly validate paths that terminate at non-leaf nodes. To fix this, add a condition to confirm that the current node is a leaf before concluding sequence validity. Another issue is overlooking time complexity bounds. Brute force solutions can quickly become inefficient for larger trees or sequences, leading to time limit failures. To address this, design optimized solutions that prune invalid paths early using techniques like backtracking. This allows you to eliminate unnecessary computations and keep your solution efficient. Understanding the bigger picture can also help you excel in interviews. This problem is a great example of combining recursive depth-first search with sequence matching, which is a common pattern in coding interviews. Recognize this pattern and use it to structure your solution effectively. During interviews, it's also important to discuss edge cases explicitly. For example, explain how you'll handle empty trees, mismatched sequences, or special cases like single-node trees. Comparing approaches can also be valuable. While recursive DFS is straightforward to implement, iterative BFS might be easier to debug, especially for larger inputs. Lastly, think aloud as you write your code. Clearly explain how you manage the sequence index and ensure your logic is easy to follow. For additional practice, related problems like path sum or binary tree paths can help reinforce these concepts. Finally, let's explore some alternative approaches to solving this problem. One option is iterative BFS, where you use a queue to store both the current node and the corresponding sequence index, traversing the tree level by level. This avoids recursion stack issues but may require additional memory to maintain the queue. Another approach is backtracking, where you use recursive DFS but undo any partial progress when a path is invalid. Backtracking can reduce redundant calculations but requires careful implementation to ensure correctness. For more advanced variations, dynamic programming can be considered. In cases where subproblems overlap, Memoization allows you to cache results and avoid recomputation. While this adds complexity, it can significantly improve performance for large inputs. Each of these methods has its trade-offs, so choose the one that best fits the constraints of your problem. To wrap up, we've reviewed the key aspects of solving this problem, including the DFS approach and its application. Remember, understanding the constraints and designing efficient solutions are crucial for success. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!